Understanding voltage drop is crucial in electrical projects to ensure efficient and safe operation. Voltage drop refers to the decrease in voltage along a conductor from the source to the load. Excessive voltage drop can lead to various problems, including reduced equipment performance, overheating of conductors, and potential safety hazards. Several factors influence voltage drop in a circuit, including the conductor's length, its cross-sectional area, the current flowing through it, and the conductor's material resistivity. Longer conductors naturally exhibit greater voltage drop due to increased resistance. Conductors with smaller cross-sectional areas also present higher resistance, leading to increased voltage drop. Higher current flow through a conductor results in a larger voltage drop as dictated by Ohm's law. The material of the conductor affects its resistivity, with copper and aluminum being the most common choices in electrical wiring. Copper has lower resistivity than aluminum, meaning it offers less resistance to current flow for a given size. Several formulas are used to calculate voltage drop depending on the type of circuit and the factors involved. For a direct current DC two-wire circuit, the voltage drop can be calculated using the formula voltage drop equals 2 times the length times the current times the resistance per unit length. This formula takes into account the round-trip length of the conductor. For alternating current AC single-phase circuits, a similar formula can be used, but it may also include a power factor correction depending on the load characteristics. For three-phase circuits, the voltage drop calculation is slightly different, accounting for the phase relationship between the voltages and currents. The National Electrical Code (NEC) provides guidelines and recommendations for acceptable voltage drop limits in different types of circuits. The NEC recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. Branch circuits are the final circuits that supply power to outlets, lighting, and appliances, while feeders are the circuits that supply power from the service entrance to the branch circuits. Adhering to these voltage drop limits helps ensure proper equipment operation and prevents potential safety issues. To mitigate excessive voltage drop, several strategies can be employed. Firstly, using larger conductors with a greater cross-sectional area reduces the resistance and consequently the voltage drop. Secondly, shortening the conductor length minimizes the overall resistance in the circuit. Thirdly, reducing the current flowing through the conductor by optimizing the load distribution or using more efficient equipment can significantly decrease voltage drop. Fourthly, selecting conductors with lower resistivity such as copper instead of aluminum can also help minimize voltage drop. Finally, installing additional transformers or voltage regulators can help maintain the voltage level within acceptable limits, especially in long distribution circuits. When performing voltage drop calculations, it is important to consider all relevant factors and use appropriate formulas. The NEC provides tables and guidelines for conductor properties and allowable voltage drop limits. Additionally, various software tools and online calculators can assist in performing accurate voltage drop calculations. These tools often take into account factors such as conductor type, size, length, current, power factor, and temperature. Understanding the difference between voltage and voltage drop is essential. Voltage refers to the electrical potential difference between 2 points in a circuit, while voltage drop refers to the reduction in that potential difference along a conductor. Voltage is the driving force that pushes current through a circuit, while voltage drop is the result of resistance to that current flow. Analogously, voltage is like the pressure in a water pipe, while voltage drop is like the pressure lost due to friction as water flows through the pipe. Voltage drop is an important consideration in electrical design to ensure that equipment receives the required voltage for proper operation. If the voltage drop is too high, equipment may not function correctly or may even be damaged. For example, motors may run slower, lights may dim, and electronic devices may malfunction. Therefore, it is crucial to calculate and mitigate voltage drop to maintain optimal performance and safety. Several factors contribute to voltage drop, including conductor resistance, conductor length, current flow, and power factor. Conductor resistance is the opposition to current flow offered by the conductor material. Longer conductors have higher resistance, and smaller conductors have higher resistance per unit length. Current flow is the amount of electrical current passing through the conductor. High current flow results in a greater voltage drop. Power factor is a measure of how effectively electrical power is being used. A lower power factor results in a higher current flow for the same amount of power, which in turn increases voltage drop. To calculate voltage drop, several formulas can be used depending on the type of circuit. For a simple two-wire circuit, the voltage drop can be calculated using Ohm's law, which states that voltage drop equals current times resistance. For more complex circuits, such as those with multiple loads or different conductor sizes, more advanced formulas may be required. The NEC provides guidelines for calculating voltage drop in different types of circuits. It recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. These recommendations are intended to ensure that equipment receives adequate voltage for proper operation. To mitigate voltage drop, several strategies can be employed. Firstly, using larger conductors with a lower resistance reduces the voltage drop. Secondly, shortening the conductor length minimizes the overall resistance and voltage drop. Thirdly, reducing the current flow by using more efficient equipment or reducing the load can also help reduce voltage drop. Fourthly, improving the power factor by using power factor correction capacitors can reduce the current flow and voltage drop. Finally, using separate circuits for different loads can help distribute the current more evenly and reduce voltage drop. When designing electrical systems, it is important to consider voltage drop to ensure that equipment receives adequate voltage for proper operation. By calculating and mitigating voltage drop, you can prevent equipment malfunction, reduce energy waste, and improve overall system performance. It is crucial to understand the underlying principles of voltage drop and to apply appropriate formulas and strategies to minimize its effects. Consulting the NEC and other relevant standards and guidelines is also essential for ensuring compliance and safety. In addition to the formulas and strategies discussed earlier, there are several other factors to consider when dealing with voltage drop. Firstly, the temperature of the conductor can affect its resistance. As the temperature increases, the resistance also increases, which can lead to a higher voltage drop. Therefore, it is important to consider the ambient temperature and the operating temperature of the conductor when performing voltage drop calculations. Secondly, the type of insulation used on the conductor can also affect its resistance. Some types of insulation have a higher thermal resistance, which can cause the conductor to heat up more quickly and increase its resistance. Thirdly, the presence of harmonics in the electrical system can also contribute to voltage drop. Harmonics are distorted waveforms that can increase the current flow and voltage drop in the circuit. To mitigate the effects of harmonics, harmonic filters can be used to reduce the harmonic content in the system. Fourthly, the use of transformers can also affect voltage drop. Transformers are used to step up or step down the voltage in a circuit. However, they also introduce some voltage drop due to their internal impedance. Therefore, it is important to consider the transformer impedance when performing voltage drop calculations. Fifthly, the grounding system can also affect voltage drop. A poor grounding system can increase the impedance of the circuit and lead to a higher voltage drop. Therefore, it is important to ensure that the grounding system is properly installed and maintained. Sixthly, the use of adjustable speed drives, can also affect voltage drop. ASD are used to control the speed of motors. However, they can also introduce harmonics and voltage fluctuations into the system, which can increase voltage drop. To mitigate these effects, line reactors or other harmonic mitigation devices can be used. Seventhly, the location of the load relative to the source can also affect voltage drop. Loads that are located further away from the source will experience a higher voltage drop due to the increased conductor length. Therefore, it is important to consider the location of the load when designing the electrical system. Eighthly, the diversity factor of the load can also affect voltage drop. The diversity factor is the ratio of the maximum demand of a load to the sum of the individual loads. A lower diversity factor means that the load is more constant, which can lead to a higher voltage drop. Therefore, it is important to consider the diversity factor when performing voltage drop calculations. Ninthly, the power factor of the load can also affect voltage drop. A lower power factor means that the current flow is higher for the same amount of power, which can lead to a higher voltage drop. To improve the power factor correction capacitors can be used. Tenthly, the type of load can also affect voltage drop. Different types of loads have different impedance characteristics which could affect the voltage drop in the circuit. For example, inductive loads such as motors tend to have a higher voltage drop than resistive loads such as heaters. 11thly, the use of surge protection devices, SPDs, can also affect voltage drop. SPD are used to protect electrical equipment from voltage surges. However, they can also introduce some voltage drop due to their internal impedance. Therefore, it is important to consider the SPD impedance when performing voltage drop calculations. 12thly, the age of the electrical system can also affect voltage drop. Over time, conductors can corrode and their resistance can increase, which can lead to a higher voltage drop. Therefore, it is important to periodically inspect and maintain the electrical system to ensure that the conductors are in good condition. 13thly, the presence of nonlinear loads can also affect voltage drop. Nonlinear loads such as electronic devices draw current in a non-sinusoidal manner, which can create harmonics and increase voltage drop. To mitigate these effects, harmonic filters can be used. 14thly, the use of renewable energy sources such as solar panels can also affect voltage drop. Solar panels generate direct current, DC, electricity, which must be converted to alternating current, AC, electricity using an inverter. The inverter can introduce harmonics and voltage fluctuations into the system, which can increase voltage drop. To mitigate these effects, proper filtering and grounding techniques should be used. 15thly, the use of energy storage systems such as batteries can also affect voltage drop. Batteries can be used to store excess energy and release it when needed. However, they can also introduce voltage fluctuations and increase voltage drop during charging and discharging. To mitigate these effects, proper charging and discharging control strategies should be used. 16thly, the presence of electromagnetic interference, EMI, can also affect voltage drop. EMI can induce currents in the conductors, which can increase voltage drop. To mitigate these effects, shielded cables and grounding techniques should be used. 17thly, the use of power line communication, PLC, systems can also affect voltage drop. PLC systems use the power lines to transmit data. However, they can also introduce noise and distortion into the power lines, which can increase voltage drop. To mitigate these effects, proper filtering and shielding techniques should be used. 18thly, the use of wireless communication systems can also affect voltage drop. Wireless communication systems can induce currents in the conductors, which can increase voltage drop. To mitigate these effects, proper grounding and shielding techniques should be used. 19thly, the use of LED lighting can also affect voltage drop. LED lighting is more energy efficient than traditional lighting. However, it can also introduce harmonics and voltage fluctuations into the system, which can increase voltage drop. To mitigate these effects, proper filtering and control techniques should be used. 20thly, the use of electric vehicles, EVs, can also affect voltage drop. EV draw a large amount of current when charging, which can increase voltage drop in the electrical system. To mitigate these effects, dedicated circuits and charging stations should be used. 21stly, the use of smart grids can also affect voltage drop. Smart grids use advanced technologies to monitor and control the flow of electricity. However, they can also introduce complexity and increase the potential for voltage drop. To mitigate these effects, proper planning and control strategies should be used. 22ndly, the use of microgrids can also affect voltage drop. Microgrids are small-scale power systems that can operate independently or in conjunction with the main grid. However, they can also introduce voltage fluctuations and increase voltage drop. To mitigate these effects, proper planning and control strategies should be used. When selecting a conductor size, firstly determine the ampacity requirement. The ampacity of a conductor is its current carrying capacity, which is the maximum amount of current that a conductor can safely carry without exceeding its temperature rating. The NEC provides tables that list the ampacity of various conductors based on their size, material, insulation type, and installation conditions. To determine the ampacity requirement, you need to calculate the total load that the conductor will be supplying. This includes all of the appliances, lighting, and other equipment that will be connected to the circuit. Secondly, calculate the voltage drop. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. To calculate the voltage drop, you need to know the length of the conductor, its resistance per unit length, and the amount of current that will be flowing through it. The voltage drop can be calculated using the following formula: voltage drop equals current times resistance. Thirdly, consider the ambient temperature. The ambient temperature is the temperature of the air surrounding the conductor. The ampacity of a conductor decreases as the ambient temperature increases. Therefore, it is important to consider the ambient temperature when selecting a conductor size. The NEC provides correction factors that can be used to adjust the ampacity of a conductor based on the ambient temperature. Fourthly, consider the number of conductors in a raceway or cable. When multiple conductors are installed in a raceway or cable, their ampacity must be derated. This is because the heat generated by the conductors can raise the temperature inside the raceway or cable, which can reduce the ampacity of the conductors. The NEC provides derating factors that can be used to adjust the ampacity of conductors based on the number of conductors in a raceway or cable. Fifthly, consider the type of termination. The type of termination used to connect the conductor to equipment can also affect its ampacity. Some terminations are rated for higher temperatures than others. Therefore, it is important to use terminations that are rated for the temperature of the conductor. Sixthly, select the appropriate conductor size. Once you have considered all of the above factors, you can select the appropriate conductor size from the NEC tables. It is important to select a conductor size that is large enough to carry the required current without exceeding its temperature rating or the allowable voltage drop. Seventhly, verify the conductor size. After selecting the conductor size, it is important to verify that it is adequate for the application. This can be done by performing a voltage drop calculation and checking the temperature rating of the conductor and terminations. Eighthly, consult with a qualified electrician. If you are unsure about any aspect of selecting a conductor size, it is always best to consult with a qualified electrician. They can help you determine the appropriate conductor size for your application and ensure that the electrical system is safe and compliant with the NEC.